Okay, I suppose we can get started. And I didn't put it on the overview slide, but you can see here obviously what we're going to be talking about. But we could start with some questions about this exercise number 3, if there are any questions about that. Just as a reminder, the exercise is due by the end of the day tomorrow, so you'll still have the chance if you need some extra help to get that in the exercise work time tomorrow afternoon. But are there any questions at the moment about exercise 3? How does it seem compared to the earlier exercises? About the same? Bit easier? Bit harder? What do you think?
Questions were a little bit unclear.
Yeah.
Okay.
Just like what they're referring to exactly, because they said like find x on some map. It's like on which graph do you want? And there was like max slope. And it was like, okay, which graph of max slope do you want?
Yeah. Yeah. Okay. So there's a little bit of ambiguity about some of the questions.
These questions that seem reasonable, like the value for time scale. Like I still don't understand if they're reasonable or not, because like I don't have much experience of timing, so I don't know with what to compare it.
Yeah.
So I thought like it's maybe a little bit bigger, but because we didn't count other factors, but I'm not sure if it's like I don't know.
Yeah, well, I think, I mean, the question of does it seem reasonable, for instance, with the time scale for the characteristic time for diffusion. Yeah, it's mostly like if you think about it as a geological process, do you have a number that's on the order of like millions of years? If so, then it's perhaps reasonable. You wouldn't expect that if you change something like the uplift rate for some landscape that's 10, 20 kilometers across, that it should respond to that change in 30 seconds, right? It takes quite a long time. You get a big number for the characteristic time when you start dealing with a big landscape, and that's the question is mostly just like, does it seem like it could be a reasonable number for a geological time scale?
So the question about order.
Yeah, I mean, it's really just, does it seem like it makes sense to you? Can you understand it if you think about this as a geological process, that landscapes don't immediately respond to changes in different parameters? So it can take some time, and obviously as the landscape gets bigger and bigger, it takes longer time to adjust to a change. So compared to the earlier examples where we were dealing with this like 100-meter distance between the rivers, that responded much more quickly to a change than the case when we now have like 20 kilometers between the rivers. That's the idea. Yeah.
Questions you have question 1, and then there'd be 3 questions within it. It's being half a mark, and it seems a bit, I don't know, write the days on them.
Yeah.
They're only worth not that much. It's kind of hard to tell when they're all kind of compounded like that.
Yeah, I mean, to be totally honest, I'm not sure in the future what I'm going to do with those kind of questions that are in there, because it's good thing to sort of stop and reflect on what you've done, and to think about like, okay, in the context of geological processes, does this idea of what we've been doing, like, do I understand it? I have almost thought about not having them be worth points at all, just as kind of like a self-reflection, self-assessment sort of, what are you thinking at this stage? And you could just get some feedback from the graders then about like what you've said there. But if you make it worth no points, then people would most likely just skip doing it altogether. And so I'm a bit torn, because like, yeah, I do understand that like they're not worth that much in terms of the number of points, especially if it's like 3 little questions that are part of a half-point question. But yeah, I think the thing I also want to emphasize in terms of the points is more like the coding part of the exercise. So it gets difficult. I mean, I think the questions are important, but I haven't found a good solution for how to balance things. So yeah, I understand exactly where you're coming from, because it's something we think about too with making the exercises. So yeah, if anyone has any ideas about that, perhaps at some point I'll ask for some feedback and see if you have any suggestions of whether you think it would be worthwhile to have them maybe just overall be worth some amount of points for all the exercises, like just that you get, you know, an exercise worth of credit at the end for all the questions combined, just as reflection questions, but I don't know.
I think it's okay. Like for me, it's okay. Points is okay. Questions is okay. Sometimes it's unclear, but like about meaning of question. But it's like a good idea to like reflect what we've done. So
yeah,
for me, it's okay.
Yeah.
It's just I got on the quarter of the mark deducted for one tiny word in one question.
Yeah.
That kind of defeats the
Yeah. No, I understand.
I understand that it's supposed to be reflective and supposed to understand it, but I've done the stats like 6 years ago now.
Yeah.
I remember what the artifact
Yeah.
is.
Yeah.
Sorry.
Yeah, no, I understand, and it's yeah, I mean, it's also something like we suggest to the graders to be fairly liberal with like not taking off points, but in some cases there's a question where like I've given the answer as like it should be this, and if they get something different, then yeah. So okay, yeah, any other things about exercise 3, or shall we move forward? All right, so we're on to talking about the advection equation this week, and we'll define that in a moment, along with exploring our application for this week. But basically, we'll do the same thing like we did last week. We'll introduce the equation first, and then talk about how it can be applied to a geological process. And again, like the diffusion equation, there's a number of different places where you could apply the advection equation. In this case, we'll stick with this sort of geomorphology theme and apply it to bedrock river erosion, but we could just as easily apply it to heat transfer processes or other processes. But you can see here in this little animation a kind of nice example of what advection is as a process, and basically it's just transport of some quantity, lateral transport of some quantity. Here, what you can see in the colors, as you could probably well imagine, is temperature. And so this is a model of convection of, I guess, the scale of the mantle of the Earth. And so you can see relatively cold bits of material sinking down from above. These would be like a subducting plate in this type of model, as well as relatively warm regions where you have upwellings of material that would be something like a plume rising in the mantle. And the basic idea with this is that as the material is flowing along, as the material sinks down from the Earth's surface, it carries with it its thermal energy, its heat, and it's transferred down into the interior of the Earth. And you see that as a result then that these areas that are sinking down, the blue regions, they do start to warm up over time, but they sink down and carry with them the signature of being cold near the surface down to significant depths. In some cases, you can still see the temperature anomaly all the way at the core mantle boundary of some cold material that has sunk down before it eventually gets warmed up and potentially could then be cycled back up to the surface. But this is basically just physical movement of this, I don't know what this could, could this be a plate if we want to think about it this way? Movement of that plate and the subduction of the plate into the interior of the Earth. And in this case, the heat transfer process is not something like atoms of material that are interacting with one another and transferring heat and transferring thermal energy that way, but rather physically moving and subducting or translating the plates around on the Earth's surface. Now, as a reminder for our diffusion equation last week, we saw basically two pieces. We had this flux being proportional to a gradient part. That was basically the equation here, where we said our flux Q was proportional to the slope or the gradient in the topography, so dH dx, plus some coefficients that are out in the front here, density and the diffusivity, that were just some numbers that you could stick out in front of this equation. So the proportionality thing before, we basically didn't have these constants, but we can define diffusion in this way. And the other part was the conservation of mass or conservation of energy, whatever our conservative part of our equation. that says that any change in the flux will be resulting in a change in mass or energy. And that is basically shown here where you have this dH dt. So if you think about this in terms of elevations of the Earth's surface, this would be change in elevation over time being equal to 1 over the density times the change in flux over some change in distance. And we looked at some examples of how that worked last week. Now there's a Q here and there's a Q up here, and you can actually plug these two things in together. This is what was gone through in the lecture notes that you may have looked at on the course page about solving the diffusion equation. Basically stick those two pieces together and you end up with something that looks like this, where the change in elevation over time is proportional to this, or equal to the diffusivity times the second derivative of the elevation with respect to x. So second derivative of h with respect to x. And this is the sort of classical form of the diffusion equation. That was our starting point for the equations we dealt with in the exercise about making these diffusion governed hill slopes that sort of look like a parabola in terms of the geometry. There's a bunch of different letters here that we don't need to worry about in too much detail at the moment, but this is our diffusion equation. And this is all stuff that we had seen last week. Now, if we compare it to the equation we're going to meet this week called the advection equation, things look somewhat similar. We can put it in the same terms in terms of dH dt. So we'll consider, in this case, again, change in elevation at some location over time being equal to a constant c times dH dx. So in some sense, this is a little bit simpler. We have only here a slope or gradient in topography, or gradient in elevation, times some constant c. And between the two, the only difference, or the only obvious difference here, would be that this is a first derivative rather than second derivative for the advection equation. And well, what does that mean? Well, there's two things that are significant, and two significant differences here. One is that we have our change in mass or change in energy with time that's proportional to a gradient rather than curvature. So second derivative would be the curvature of a field, or the change in the gradient. Here we have it only equal to the first derivative, so dH dx rather than d2h dx2. So that's one significant difference. And here our advection coefficient c will have units of length over time rather than length squared over time, and that probably makes sense because that would balance out the units with the way the equation is presented. So length over time will be typical units for this constant c. Now, at least for me, I tend to look at things and understand them a bit better with a picture than I do with an equation, especially the first time I see the equation. So we can look at this now as well and consider how a river channel profile would change if it was a diffusion process versus an advection process. And first off, I guess we should establish what is a river channel profile. Have you seen river channel profiles before? How many have not seen river channel profile before? Okay. So yeah, basically this is just, if we took a river and just looked at how its elevation changes as you go along its length, that's what we're looking at here. So we have here at time 1 some river channel that goes along some relatively shallow gradient, kind of low slope area up here. Then it gets steeper for the channel, and then it flattens out again. So you could think about this as being kind of typical river that you might see somewhere in, well, most relatively flat places, and then some rapids, and then relatively flat, shallow gradient river again. Now, if this river is being governed by a diffusion process, which is often the case for rivers that are full of sediment, what generally tends to happen is that the areas where you have this sort of increase in the river gradient, you tend to see a lowering of elevations, and then where the river gradient is going from steep to relatively shallow, you see elevations that are typically going up. And this has to do with the fact that as the river velocity slows down, the sediment that's being carried by the river can no longer be moved by the water, and it gets deposited. And that tends to basically do something like this, where you can see that when the relative to the elevations that we had initially, where the slope is decreasing, or sorry, where the slope is increasing the most, we see lowering of the elevations. Where it's decreasing, we see elevations going up. And of course, you go further ahead in time, eventually what you'll see is that there's a tendency to try to smooth out this change in the river slope over its length. And this applies to rivers that would be alluvial rivers, so rivers where you've got sediment more or less covering the channel bed and can easily be moved around. We can consider another example here if we look at our advection equation and how the advection equation would work for this river channel based on the form that we have over here. And that would be that if we start out with our channel profile that looks like this at some time t1, as we go forward in time, the change that we see here is not a change in the shape of the channel profile, but just a change in its position. It's basically being moved off, in this case, to the left over time for water that would be flowing off to the right. But it's keeping the same geometry. And so over time, it's not like the slopes are getting less steep. It's just simply moving laterally off to the side. So it's kind of like it's eroding into some higher elevation landscape over time. And this is what's often seen for bedrock rivers, is that they tend to follow this sort of advection type erosion law that leads to channel profiles that might look something like what's shown here when eroding into a plateau margin or something like that. So slightly different form of the equation, and the difference really here is that we have a kind of different behavior. Whereas we're changing the shape of the channel profile here, we're not really changing it so much in the case of the advection equation as it's shown here. And we'll get to some additional important geological considerations that will have to do with this constant C in just a moment. But that's our general picture. For diffusion, basically our rate of erosion depending on the change in the hill slope gradient or the curvature. So you can see the areas where the curvature is high, where the slope is changing the most, are the places where the elevation changes the most. And you can see that kind of nicely where the break in slope happens here in channel at T1, and that's the place where the elevation has changed the most later in times T2 and T3. For advection, because our rate of erosion is directly proportional to the slope, that leads to a behavior like this where you just keep the same geometry and move it horizontally, in this case, to the left with time. And in addition, we have no conservation law here that's connected with our advection equation, so there's no need for material that is removed from some part of the channel to be deposited elsewhere. The idea with the bedrock river is that generally the water is able to transport the sediment more efficiently than, well, it's able to basically keep the channel bed clear of sediment because there's enough power in the river as it's flowing over the landscape. So sediment that's eroded from some part of the landscape in these bedrock rivers is just flushed out downstream somewhere, and it's deposited elsewhere where the river is not having water flow over kind of fairly bare bedrock. So a little bit different assumption for how the model's working as well. If we want to think about this in a little bit even more simplified world, we could look at our equation here basically as dH dt equals c times the slope dH dx. So in this river channel profile, we'll consider here at time 1 our channel that looks like this with the gray line. So it's flowing totally flat, then has a constant slope, and then totally flat again. Obviously, this is a sort of cartoon example. But the idea would be here that if the slope is 0, there should be no change in elevation. And you could imagine that a river that's flowing on a totally flat surface, well, you probably wouldn't call that a river at all, but the water's not moving, and so it has no potential really to erode the channel underneath it. Okay, maybe there would be some kind of chemical interaction between the water and the bedrock that could be happening, but there's no physical, there's no mechanical erosion of the channel underneath the water in these flat bits. Same thing would happen down here, right? The only place where there's going to be any action would be where the river has some slope. And you can easily imagine that in thinking about how natural landscapes work as well, that when you put water on a slope, it tends to flow downhill. As it flows downhill, it has potential to pick up sediment and transport material downstream. So we see that in our equation here as well. In this case, where the slope is has a negative value, we see a lowering of elevations of the landscape. So dH dt would be negative, which means that our landscape would be getting lower. That makes sense. And the idea here is that we would have some, between one time and another, with the way this equation would work, we would have our landscape go from this gray line to the blue dashed line over time. So basically this kind of eroding into a plateau type thing that we saw before, where this value of C is basically how efficiently the bedrock is being eroded. So if you take C and multiply by some time step dt, that would basically show you how far the river would have moved over that time. And from that, you can see just by the river moving to the left over time that you get some change in the elevation of the river at any given place. So if you were to sort of hover above the surface of the earth at this location, as this was happening, what you would see is that the river is moving off to the left, but as a result, the elevation of the channel with respect to the earth's surface is getting lower, and that's what the blue arrow there is meant to indicate. So obviously, this is just an explanation of how this advection equation works, but we don't see landscapes that look that much like this. We don't see river channel profiles that look like this in nature. And so there's some additional complexity that we need to consider here when we think about how rivers work in natural systems. So what we're going to look at now is basically applying our advection equation to erosion of bedrock by rivers. And this is going to be something that would apply to landscapes that look maybe something like this, where we've got, this is some nice national park in Western Canada, where there's a river that's flowing over a relatively flat part of the landscape and then comes to a waterfall and flows through this kind of little canyon here, and that would be a place where bedrock river erosion would certainly be happening. And that's to say that we're in, this is in contrast to other parts of the landscape. So, this might be some relatively mountainous region, but if you go down into the foreland out in the front of where the highest elevations are, what you often see are these kind of braided rivers. So rivers where you have many different small channels separated by sediment that's being deposited and moving sort of continually across a relatively wide region. You can see pretty nicely here that basically everything that's this sort of lighter gray color here is sediment that's going to be moved around at various times depending on how much water is in the river system. So we're not looking at this, though. This is the kind of alluvial rivers where the diffusion equation might be more appropriate. We're not looking at that. We're looking at these bedrock rivers, so places that would be higher up in mountainous landscapes where essentially you have water flowing over the bedrock with limited amount of sediment beneath it. And so you can see here, even in this picture, so this is from the Kali Gandaki River in central Nepal. Just took a picture off of Wikipedia for a nice example. It's not like there's no sediment in the river. Obviously, there's big boulders and things like that that are being slowly moved downstream. But what you have here is an insufficient amount of sediment to kind of protect the bedrock under the water from being eroded. So this is where the equations we'll be looking at today can be applied most appropriately, would be these kind of bedrock rivers. So what we saw before with our bedrock river in terms of its evolution over time is what's shown here also, where the shape of the channel profile is basically the same from time 1 to time 3, just moving off to the left as this landscape is being eroded. And that's what we would predict if we have a constant advection coefficient. So if our value for C in the equation is a constant, this is exactly the kind of scenario that we would predict. What do you think about this? Do you think this works for natural rivers?
Over like a million years or something like that. Talking about rock, it's not gonna like erode super quickly, nor do you see like, I don't know, huge cliffs which is like have such a steep gradient from where they used to be. You probably would see more cutting off like the bed once the river like flows down. You'd see that from the cutting down, but unless like it happens so much that the overhang would fall down into the river. I'm not sure it would happen.
Yeah. Yeah, so I think, I mean, maybe there are some places where this process can work as it's shown here in the picture. But what are some other things that might affect this rate of, well, what it's called here lateral migration, but what might affect, you know, a river being able to erode into an elevated landscape? I mean, here, the picture basically shows that this thing would continue moving off to the left for some infinite amount of time. If we kept going for T4, T5, T6, this river profile would still keep moving left. But eventually, we know in natural landscapes that we don't see rivers that just completely erode mountains out of the way. So what is it about natural rivers that might limit their ability to keep eroding?
Like some more hard rock.
Yeah, so the sort of strength of the bedrock. If the strength of the bedrock varies, you may have resistant bedrock lithologies that aren't eroded very easily. So that's certainly one.
Size.
So what do you mean by size?
Like scale, because this picture more looks like for a big basin or something like that. So for big basin it's neutral forms, but for small river it's not neutral form.
So yeah, I think size will matter. What is it about the size that might be important for how efficiently a river could erode?
It's about space of ability to contain sediment.
Yeah, that's maybe one part of it. What can you think of something else that might matter about like the size? If we look at a river basin that's really small versus a really big river basin, what's going to be different?
Amount of water.
Yeah, the amount of water, right? So how much discharge you have in the river is going to scale with how much drainage area do you have to capture water, right? The bigger the area is, the more potential you have to.
That's what I meant about space.
Yeah.
It's always called like space. It's ability like to contain sediments. It's like amount of water and space between like bottom and top of sea level.
Yeah, exactly. So we're going to have this, the strength of the bedrock might matter. The amount of water in the river is going to make a difference. And how is the amount of water going to vary, for instance, if we go from this high elevation part of the landscape downstream? How's the water, the sort of discharge, how might that vary?
Forces to replace sediment, like the more velocity of water, the more forces to replace some big particles, right?
Yeah, so that's almost another question. You're right, because like there's going to be an effect of the slope too. But like, let's imagine that this is the drainage divide between two rivers that would be flowing off to different directions. What's the discharge in the river if you go just, you know, one step from the drainage divide? Compared to if you walk way down here, how's the discharge going to be?
Can I just ask,
Yeah.
so this diagram, that is like over the total course of the river. It's not like a bed profile then.
No, yeah, this is more like the length from, you know, starting at the beginning of what you could call
Yeah.
the fluvial system
Okay.
and following it downstream to, you know, where it might hit.
I thought it was like
ocean.
a riverbed. I was like, I've never seen something like
Yeah,
that.
no. So yeah, this is like so this would be kilometers
Okay.
or hundreds of kilometers scale.
Okay.
So like, let's imagine you're standing right at the drainage divide on some ridge, and you take one step, you know, from that position, and you say, okay, how much discharge would I have? How much water would I have in my river system there, compared to if you went down to?
You mean water pressure or?
I mean, basically, how much water is there? Like, if you go along this river channel profile and you just say, okay, how much water's in the river system now? How about here? How about here? How's it changing?
Increasing, it's not about water, the pressure of water. It's
No,
like
but I think, I mean, the basic idea here is that, you know, in a natural river system, as you go from the highest elevation, you're always increasing the amount of water you have in the river, in the, you know, assuming that you don't have some weird situation where, you know, you've got more evaporation than you have precipitation when the, if we assume that it's a sort of humid landscape or humid area where we don't have to worry about complications like that or water being lost to, you know, groundwater in significant volume. Basically what's happening as you go along the river is that you're getting more and more water as you go further from the drainage divide. That's also going to be important because as you put more water into the river system, you have more potential to move sediment. You have more potential to erode. And the slope obviously will matter as well because we've seen that already. So there's a couple things that matter. The discharge, as we've been pointed out, slope, and the bedrock strength. We basically hit all three of those big factors. So if we want to try and look at natural river systems, we have to then consider how the discharge or how the amount of water in the river will vary along the length of the river, how the slope changes, and what the strength of the bedrock is. There's also other factors that can go in there.
Surely this diagram is assuming that the material the bedrock is, or the material the bed is made out of is going to stay the same, like through the whole time process.
That's right, yeah. So here, the assumption in the picture like this is that, yeah, the erodibility of the bedrock is constant. Of course, that's also not true in natural rivers. And so, you know, these are all things that will affect things like natural channel profiles that are not being considered here, because we're going to start with the sort of simplest picture we can have. And of course, none of these things are going to be constant. The amount of water in the river, the slope, the strength of the underlying bedrock in terms of its erodibility. So basically, the equation that I introduced at the beginning, we can't use this one to model natural landscapes, at least not in this form. We can't just say there's one constant C, and we multiply by the slope, and that tells us how natural rivers erode. Instead, we use a slightly more complicated equation, and even this is really oversimplifying a lot of things, but basically saying, here, let's take C and divide this into a few different constants. Q is one of the big ones, that's the discharge. So we just go along the river and say at every point how much water is in the river. KF is some material property related to the bedrock erodibility, so how easily the river can erode the bedrock. And W would be channel width in this form. Obviously, the wider the river is, the thought is that you have distributing this water in a different way. Very wide river with the same discharge versus a very narrow river, you will also affect how easily the bedrock can be eroded. And often you see things like canyons where rivers tend to get quite narrow because they're able to then carve into the landscape pretty efficiently. So this equation here is what's called the stream power erosion equation. Maybe you've seen this before, I don't know. But it is basically an advection equation You probably would not have been introduced to it in that form, but essentially that's what it is. It's just a form of an advection equation, because you can see we have dH dt being proportional to dH dx with some constants out here related to our river example and a river application here. So we can make a couple assumptions and make this equation look a little bit different, even though it's still showing basically the same thing. We'll put it into a form that's much more commonly used by people who study things like natural river channel profiles. And that is to simplify things a little bit by taking our discharge, and instead of using the letter Q for a discharge, which would then have to be calculated for a natural landscape, if we want to just look at a river channel profile, we can actually calculate it based on some estimate of the area upstream from some location, if we assume that the amount of rainfall is constant across the landscape that we're looking at in this case. So if we can assume that, then we can just take the area and say if we know there's constant rainfall, we can find the discharge from knowing how big the drainage basin is. We can replace our dH dx with the letter S, so that's just standing for slope, but that is basically just dH dx. And now instead of these different constants out in front here, we can lump them all together as a big K, which is referred to as the erosional efficiency factor, but accounts for lithology, climate, channel geometry, sediment supply, and many other factors. This is basically just a garbage can constant that accounts for a very large number of different things that vary in natural systems. And then these letters M and M and N are slope exponents that are often used and sort of calibrated from natural landscapes. So you can basically solve for M and N if you have natural river profiles, and learn things about like your erosion rate from that. This estimate of the area is often done also with a somewhat semi-empirical calculation. Basically just says if you go along the length of your channel, some distance x from the drainage divide, and raise x to the power 5/3, that gives you an estimate of how big the drainage area would be upstream. So it's a way of basically only considering things along a profile and getting an area just from knowing how far you are from the drainage divide. And so now we can test ourselves a little bit here about our thinking. We have our example of the stream power erosion law here. This K times A to the M, so area to some power M, slope to some power N. And we can assume that those are both equal to 1 for the moment. But based on our stream power law, if we look at some channel that initially looks like this, just constant slope flowing downhill, and in a landscape it's being uplifted at some velocity u, but it's uniform everywhere. What do we think this would look like over time? How would this, would the shape of this channel profile change over time? And you can think about this in terms of some of the factors here, how they might vary along the length of the profile, and then how the slope might change as you go along values in x. Why don't we take just a moment, and you can either think about this on your own, or if you like, or I would certainly prefer if you want to talk with your neighbor just a moment and speculate about what you think this this channel profile would evolve to look like after some period of time when there's erosion happening. Why don't you think about that for a moment, and then we'll come back and see what your ideas are. So the question is what this looks like at some period in the future, when it starts out with just a constant slope. So you can think about these different letters in here. K, we can assume is constant, but A might be changing along the length of the profile. S might be changing along the length of the profile. And you could think maybe about how those might change.
But like we don't have like any uplift at all in the UK because we don't have any tectonics. So like everything that was eroded is like pretty much just
Yeah, the same as my place.
yeah.
No, not different at all. Okay, so if we like decrease like our A,
Yeah, if we say that it gets larger the further down it
yeah.
goes.
So it will equalize it, like not equalize. It will decrease the that slope.
Yeah. But I think it's just gonna get like less steep.
So the more forces equalize U, the more close like it will be to zero. So the more flat we will have relief, as I understand.
Yeah, because like I don't know whether uplift will be from one. Would uplift be constant over the entire plane?
We'll assume that,
Okay.
U is constant everywhere.
Okay. Because then you're gonna have like if it was like that before, I think it'd probably be like more like that.
Yeah.
Afterwards.
Yes.
If it's like if it was uplift here, then it would like rise.
Yeah, so to make this territory flat, we need to equalize like uplift with all these
But yeah, like when I do the function definitions,
variables. So
Well, listen, if you're gonna have more sediment, then you're gonna
yeah,
more stuff down here.
yeah. So it will equalize uplift. So the more this equation, like less we have a result like when we
I still feel like it's
separation, like
not
U
too bad.
minus U.
It looks like okay, so I was like, oh my god, what was it?
Yeah.
That's why I keep saying.
It always looks like really scary when you see only letters that are not words.
Yeah.
You know? When there is some.
Will you put up the lecture slides?
Yeah. Yeah, they'll be on the course page. I'll post them probably 10-15 minutes after we finish. They should be up. Yeah. So any predictions here about how this profile might evolve? Maybe we can do it this way.
I guess you can like draw it on.
Yeah, let's do it like this. I've got
We'll do it with a pen or whatever.
at least
Which way does the pen go?
one color of chalk. I got a kind of yellow, green, sort of brownish. So let's do it like this. We assume that our channel profile, we'll just use H because that's been used in the equations, but it initially looked like some dashed line here that we could say was our channel profile at sometime t0. What are your thoughts about how this might evolve? And the key thing here is that we're assuming we've reached a steady state. What that means is that the uplift of the landscape is being balanced by erosion by the river. In natural landscapes, what that would mean in practice is that up here at the high elevations, you have almost no water in the river system. So in order to be able to erode fast enough to compensate for the landscape going up, you have to have a really steep slope. And we basically see that the highest parts of the landscape have steep slopes. So up here, we'd expect to see pretty steep slopes at high elevation where we don't have very much water in the river. As you go downstream, you're adding more and more water to your river system, and eventually reach the point where the slope doesn't need to be very steep in order to still have the same erosion or the same potential for erosion that you had up here. And so you get these nice kind of concave up river profiles. And that all comes from basically the trade-off between this increasing area and the slope that you would need to have erosion that balances the uplift rate. So with this kind of stream power equation, maybe I'll turn off the light here for a second, make it a bit easier to see. But basically what we see is that here is an example. Again, I think this is basically just a model, but the idea is that up until a certain point, a certain distance from the drainage divide, you don't really have channelized water. So there might be some rain falling on the landscape, but it hasn't been able to be organized into river channels yet until you get to a sort of big enough amount of water flowing on the landscape to be organized in channels. After that, what you see is that you tend to have fairly steep river channels where there's not much water in the river, and then that channel slope will decrease pretty rapidly once the amount of water in the river is sufficient to erode the landscape efficiently. So we'll play around with this idea in the exercise for this week, applying the advection equation, but basically doing it in the context of these river channel profiles, where you'll see exactly these kind of effects that, depending on the starting geometry of the river system and the slopes and the amount of water you have, you'll see that the river will evolve differently. But eventually, in steady state, they all kind of come to this sort of concave up shape that's quite typical of mountain rivers. I think I'll skip the recap questions because I think we've covered enough for this part today. Are there any questions about this?
Yes.
Yeah.
So yellow line is like respond to change of slope in the river, and green line change of water level? Or?
Well, so I mean, what I was trying to illustrate with the different, like with the green versus yellow, was if we considered only the increase in the area, that would suggest that if we have a constant slope and we held that constant, that the potential to erode the landscape would just be increasing as you go downstream because you're getting more and more water in your river system. If the slope is constant, then you would expect to see your river profile start to evolve in this way as you go further downstream, more erosion potential, and you lower the channel more. Of course, that isn't what we see, and part of that is that if we look at the steady state, so where there's a balance between uplift and erosion, that's where this really couldn't apply, because this would be like maybe a transient thing that might start out eroding this way, but over the long term, you tend to evolve to a profile that looks more like this, where once you have enough water in the channel, the slope or the gradient of the river gets to be lower, and that will then balance uplift, whereas in the high parts of the landscape where there's not very much water in the river channel, you need still to have a steep slope in order to basically, think about it this way, in order to perform the same amount of erosion that you have up here, in order to lower the landscape in the same amount up at the high elevations, you have to have a steep slope, and down at low elevations you have so much water in the river you don't need much of a slope to still be able to erode.
What's the green dash line?
Well, the green dash line was my attempt to account for the fact that in this picture we didn't consider this change in the slope along the length. So essentially just saying that, okay, well, we know in natural systems they don't follow a trajectory like this, and that's because eventually, once you have enough water in the river system, you don't need a very steep slope to be able to erode the landscape. But yeah, the main thing here is just to kind of have the picture of this, like why things are steep up at the high elevation areas and why they're not so steep as you go downstream, and that's basically because you don't need the channel slope to get the water moving because you have lots more water in your river. So, okay, let's, well, I can check any other questions. If not, we can take a quick look at the exercise, just so you can see what's coming with that. The course page is still, I need to push the changes for this week with the lecture slides and things like that. But exercise number 4, as mentioned, is basically about this idea of the stream power erosion, and so it's called river advection. And there's essentially only one Jupyter notebook, similar to the last week's exercise and the one before, I believe. If it wants to render, what you'll see is that we first have a couple equations that need to be converted to Python functions, sort of like what we dealt with in the previous exercises. So we have an equation here that allows us to calculate what the drainage area is along the length of some profile. And so you'll convert this drainage area equation to a Python function called drainage area. And that's the first step for the first problem, is to basically make this drainage area function. Once you have that, you can see there's some visible tests here. So that means you'll be able to check and see whether your Python function works as it's supposed to. So that's nice. There's 2 tests that will allow you to make sure it's working. And then you can move on to the next one, which is this stream power erosion equation. So you'll also make a Python function for this. And there are a couple things here that could be a little bit tricky. So you may need to get some input from us or check the hints for the exercise for this week. The A that you'll calculate comes straight from the function you have just made, so that won't be an issue, but the slope can be a little bit tricky. We have to use, you can calculate this by hand if you want, like if you want to come up with your own way of calculating slope, you can use that, but there's also a couple NumPy functions you can use for calculating slopes. One of the limitations is that, like, if you have, for instance, 10 points along some profile where you know the elevation, when you calculate the slope, you don't get 10 values back for your slope. You get 9 values back because the slope is going to be the difference in elevation between 2 points. And so you'll have to take a look at the hints about how to add an extra point in there to make sure that you get as many slope values as you have elevations, so that everything is able to be used as expected. But basically, you just make another function, and again, there's some visible tests that will allow you to check and see whether your function is working as you would expect it to. After that, there are a couple other functions that we are providing for you that you don't need to do anything for other than just run the cells so that you can do the calculations. So like I made a function here called createX. This just makes the array of values along the length of your profile where you can calculate elevations. And there's another function here called createProfile that just defines the elevation of the river channel at the start of the model. So there's one case where it's just flat with an elevation of 1 meter above sea level, except for the very last point where the elevation is 0. There's another example of like having an elevated plateau with a very steep break in slope, and then another of a constant slope along the length of the river profile. So this is just a function that you can run, but it allows you to specify different options for what the river channel elevation should look like at different times. And then these are all combined in a big function called stream power. As you can see here, we've kind of stepped it up a little bit in terms of like number of arguments, number of parameters in our function. There's a lot of different options here, Essentially, this is just like one function that allows you to put in any of the variable values you might like to explore when using the stream power equation. And the code is basically here for you, and you don't need to do anything to this part of the code. I'll just go over this very quickly to kind of give you an idea, but the hope would be that you'd spend a little bit of time just reading through this at the start to see, for instance, here, there's descriptions of what each of the values are. So like what min elevation, max elevation, what all these things refer to. But before you start into the exercise, it would be good just to read this over and sort of see that you can understand what the different things in different parts of the function are doing. So at the beginning, all we do is start out by making an array of x values. So this will allow us to define the points at which we're going to calculate the elevation. And we also create something called dHdt. So that's just the change in elevation for this stream power erosion function. It's just an empty list of 0 values at the start. But that'll allow us to calculate what the erosion rate is at each point along the channel profile. And then elev is just the elevation of the channel. And that's coming out of this create profile function. So that allows you to kind of define what the river channel profile should look like at the beginning. Once you have that, you can calculate what the drainage area is. And so that's just using the function you would have created. So nothing fancy there. Then there's an uplift rate that's defined of, in this case, 1 millimeter per year. And then the uplift rates are just put into an array so that at each point of x, you know what the uplift rate is at that point. We'll come back to that in part 4 of problem 2. Then, because we've been doing stuff in pandas, we'll stick with doing stuff in pandas and put our x as our index value, and then put the elevation data into a pandas data frame called profile. So this allows us to plot the results pretty easily. Then there's a couple small calculations in here you don't need to worry about too much, but there's something where there is a variable called nplots. I'll say what that means in a minute, but basically it allows you to determine how many times you want to see the river channel profile at different times. And then essentially what happens in the code is it just loops over however long you want to run the river erosion model and updates what the channel profile looks like at each time. So it calculates, for instance, what the erosion rate distribution should look like, and then changes the elevation as a result of erosion plus uplift of the landscape, and then increases the time by some time step dt. There's a little bit in here after that then that's basically just checking to say, like, should a plot be generated at this time? If so, what it's going to do is produce a little string here that's just the string value of time. So if it's 200,000 years, it would just make 200,000 years as this variable called string. And then by using this little pandas data frame trick, profile with the variable name string, we'll create a new column in our pandas data frame with the name of the column being whatever, 200,000 years or whatever it is. And it'll store the elevation of the river profile at that time. So this is just a nice way to keep our river profile history in our data frame called profile. After that, you can plot the results, and the only thing I want to point out here is that we will be using this pandas bokeh plotting thing. If you remember back to lesson 7 from the GeoPython course, we introduced this interactive plotting thing for pandas bokeh. It's almost a drop-in substitute for plotting in pandas, but because it's interactive, it does offer a few benefits that will be, I think, helpful to you. So you have an example here of how to make one plot, and we don't need to go through here in great detail, but basically you can specify things like the x limit, so the range of values on the x-axis. The labels, x and y labels, can actually be specified in here in the plot command for pandas bokeh. Legend location can be specified here. It's pretty intuitive how the naming goes. bottom left, we'll put it on the bottom left. If you put top right, it will put it in the top right. So depending on some of the plots and what's shown, you may want to move the legend around, and you'll see in some cases, like it'll look really nice in one case, and then you run the model with the slightly different parameters, and the legend is covering up all the interesting stuff you want to see, so you may need to move it. The X ticks here is just the tick spacing along the X axis. I specified it here manually just because it looks like crap otherwise. I don't know how Bokeh figures this out, but it's like tries to put 100 X labels on and they all overlap. It looks awful. So you don't need to change this, but just so you know what the X ticks means. And then fig size is just similar to the fig size thing for normal pandas plotting, except it's given in pixels instead of inches. So this is not doing 800 by 600 inches, but 800 by 600 pixels. So just be aware of that, because if you put in 12,8, you won't see a figure, and you might be wondering what happened. It's because it's too small to be displayed or be visible. So again, I put that in there manually for you just so that you have a working example, because it could easily be confusing. So all you're doing in that first problem is you make the two functions and then you answer a couple questions. And the questions come from looking through the stream power function and kind of, what things make sense, what don't. Problem 2 is where you start using this stream profile equation. So the first thing you're going to do is basically just run the code. You just run the stream power function. You don't have to specify any parameters or anything like that. Just run it. It makes a plot, and you take a look at the plot and answer a few questions. I have an example here of what the plot looks like. So if you run your code, you should get a plot that looks like this. You can see in this example that my legend is not necessarily in a very good location, so you might consider moving it up to the top right in this example, but I'll leave it here for now. Why are we using Pandas Bokeh? Well, there's a couple things that are nice. One is you can just move the mouse along and easily figure out what the elevation of the channel profile is. That's handy, because you'll have to do a couple calculations in some of the problems about like what is the elevation in different times. Obviously being able to move this along and kind of have it show you what the elevation is for one of the lines is helpful. But the other thing is that if you click on things inside the legend, you can turn some of the lines off. So sometimes when all 6 lines get plotted at the same time, which is the default for the code working as it does, it's just a bit too busy to see what's happening. But like here, the initial profile would just be showing that we had flat initial landscape. After 400,000 years, if I click the button, I can see here what the landscape or what the river channel profile would look like at that time. And obviously, if I click the other ones, I can kind of follow along and see how things are evolving over time by turning on these different lines. In years past, this exercise, we actually used an animation function, but it was way too complicated for most of the students to understand what was going on, and it broke like every other time you'd run it in Jupyter Lab. It would break something and you wouldn't get any error output, and it was super frustrating. So we're doing it this way because I think it's not necessarily better. The animation was nice to see, and it was cool to be able to watch the river channel profile change with very small increment, but it just was a huge hassle. So hopefully this is a decent substitute. I'll just encourage you to kind of go through and if you're having a hard time understanding what's different between one problem and the next, sometimes clicking on and off the lines here can help you see how the model has changed between different times. Otherwise, it is the kind of typical interactive Bokeh environment. So like you can zoom in, you can click and drag things. If you put your, if you get your plot totally screwed up, like zoomed way out, and you're not happy with it, you can click the little reset button. That'll get you back to the original view. And if you go to one of the axes and scroll with the mouse cursor over the axis, you can zoom just in the X or zoom just in the Y range of values. So it's nice in the sense that you can play around with the plots and zoom in and explore things if you need to. So for part 1 in problem 2, like I said, you just run the code and then you answer a few questions based on what you see there. And you're given a space for that. For problem number 2, you get to add a subplot. So we're going to have our river channel profile that's generated with the plotting command here for how to do the plot with bokeh. And if this generates one plot, there is another command in the pandas bokeh library called plot grid that allows you to do subplots. You're given an example of the syntax for the plot grid here. You can use this almost exactly in your code. You do have to make some very small changes. But what that will allow you to do then is to have, for instance, your river channel profile on the top, and then on the bottom, a plot of the erosion rates along the length of the river channel. So in this case, again, this is only run for 100,000 years. This is just a static image, so I can't click on anything in here. But each one of the colored lines should correspond that like 20,000 years here would be the channel profile at 20,000 years, and then this orange line would be the erosion rates 20,000 years into the simulation. So this will be helpful in the sense that not only can you then look at the river channel profile, but you can also see what the erosion rate distribution looks like and how that changes over time. It's not necessarily that interesting when you start with a flat landscape and uplift it, but for some of the other initial topography options, it might be interesting to see how the erosion rates are changing over time. So that's basically the focus for that part of the problem, is to make the subplots. And again, what you should do here is basically just copy and paste the stream power function you have above and then start modifying it in this cell here. So I don't give you the stream power function to start with. You can just copy and paste it. And then I guess you should run it here, and maybe I need to make one small change to tell you that you should do that in this cell here, because I think it's missing some information about what you should do. So I'll fix that before I put the GitHub Classroom link live. Part 3, you can explore some of these different initial channel profile options. So like whether it's flat, sloping, or whatever, kind of plateau option. So all you do is just specify a number for which one of the topo options is, and then you look at how the channel profile looks different over the same amount of time that's in each case. So you'll use option 1, 2, and 3 and just see how the initial topography, the initial channel profile affects the evolution of the river channel. And of course, then there's a few questions after that. And then in problem 4, you are given the task of changing the uplift rate along the length of the channel. So this is like essentially the same thing as if you had a fault or something like that that was active within your river channel. So here you're going to have an uplift rate of 5 millimeters a year for values of x that are less than 50 kilometers, 1 millimeter a year everywhere else. And you'll get to then see how that has an effect on your river channel profile. Again, copy and paste the equation that you had from, or the function you had from problem 2 earlier in problem, I guess, part 2. You can copy that and then run the code here to get an example plot with this difference in the uplift velocity. Answer a couple questions and you're all done. Any questions about that? So I will quickly update the exercise to fix a couple small missing things, like maybe telling you what to do in these code cells here, and then put the GitHub Classroom link. I guess I'll put it first in Slack because that'll probably be quicker to start working that way than it takes usually a little bit for the course page to be updated and rebuilt. And then I'll put the lecture slides up as well. I think there was some other thing I was going to say that has just slipped my mind. The hints for the exercise, I'll also update those as we go. We haven't run this pandas version of the exercise before, so there are some hints there, but I think I'll probably take them down because maybe only a few of them apply for the version of the exercise that we have now. Some of them are based on the earlier animation-based exercise from last year. So the hints will be kind of being updated as we go, and as questions come up, we'll try to add some things to the hints. But yeah, any questions otherwise? It'll be maybe 5 minutes or so before the GitHub Classroom link is out in Slack, and then you'll be able to get started at that point.